basic theory for this was first proposed by Willis Lamb in 1939. He basically said that recoil, basic interactions, recoil with the lattice occurs through matrix element of this basic form. If in this day and age you're going to talk about energy transfer to and from a lattice, you better have your arguments fit in with standard theory, or else people are going to have questions about whether you're doing good physics or not. So if you write the matrix elements in terms of the coordinate positions, then you get strict recoil operator. Looks like this. But on the other hand, if your lattice happens to change in some way, if some of your bond strengths change, or if you make a vacancy, or if you turn one nucleus into another nucleus, then the lattice changes. When you do your computations, you never actually work in terms of the positions. You work in terms of what's called phonon mode coordinates. And basically, a lattice is kind of like, imagine lots of springs and masses hooked up, and the thing wiggles and rattles around. And it wiggles and rattles in certain discrete ways and certain discrete frequencies. And if you change the masses or you change the springs, the rattling is going to be different. And you need to take that into account in your theory. So it can be written this way. This thing right here is called a Dushinsky operator in honor of a guy named Dushinsky, who in 1937 treated this problem in the case of polyatomic molecules, and in fact showed that there were rather large corrections if you included those factors properly. So this bit of physics, and molecular physics is well known, even condensed matter physics, in the limit that you make first order approximations to it, there's lots of applications in condensed matter physics for this kind of effect. So there's recoil and there's mode shifting, and to some degree that's all there is. Now, if we want to shift a lot of energy, we can use either recoil or we can use mode shifting. In the case of recoil, recoil's well known. It creates phonons, it destroys phonons, which is the same thing as saying that you transfer small packets of energy, a few packets at a time, back and forth. In condensed matter physics, in solid-state physics, processes in which up to about 10 phonons being transferred are known and have been calculated out and have been demonstrated experimentally, perhaps a few more. If you take 10 phonons and you multiply it by typical phonon energy, which might be a few millivolts, 3 millivolts, 5 millivolts, perhaps a little bit more, you get a larger amount of energy, but you're not quite up to the million of electron volts that you would like to be at to transfer to nuclei. So strictly speaking, through what's known, recoil is not going to do the job. On the other hand, you can do some theory, and you can say, well, let's start with very highly excited lattice states, and let's look at the matrix elements. And in fact, you can find if you get the lattice very highly excited, you're capable of transferring more energy. And if you've done all the math and you look and you see what you've actually created, what you've found is in order to transfer the energy to or from the lattice, you've had to take something in the lattice and move it up to an MeV energy. And then if you add a little bit of energy or subtract a little bit of energy from it, then you can transfer the energy through this recoil in the way that you need to do it. And when all's said and done, that's highly non-physical. So to some degree, from my point of view, I don't think recoil can do it no matter what. On the other hand, the mode shifting behaves differently. It's well understood in the case of molecules, but not so well understood in the case of lattices. It hasn't been studied anywhere near as extensively as the recoil has. Now, the mode shifting operator turns out not to be any good at making or destroying phonons. I mean, I'd been hoping on doing this kind of thing, but that's not how it works. What it does is it takes the phonons that are there and it changes its frequency. And changing the frequency, because of the Einstein relation, it changes the energy. And consequently, your energy transfer is dependent on the number of phonons you have times the amount of frequency change that you have. This law may look a little bit like that law, but they're really very, very different. They're light years different from one another. Now, so far, the frequency shifting of the phonon, the effects are known in condensed matters. They help to make up the line shape of the Mossbauer pip. That means it's a Mossbauer effect. You get zero phonon transfer, but you get some energy transfer anyway. And that's due to this effect in part. Now, only very small energy transfers have been measured to date. The largest that have been produced or calculated or whatever, I calculated what it would be for neutron capture on hydrogen in a metal hydride, and I got it up to about 10 milli-electron volts. I could find examples in the literature that could be justifiably argued to be 5 to 10 times larger than that. But still, that's not megavolt regime either. Nevertheless, theory says that if you can put a lot of phonons into a phonon mode and then change its frequency, then you can transfer a lot of energy to and from the lattice. For example, you could imagine having the frequency change be as large as a milli-electron volt. In fact, you can find examples where frequency changes can be considerably larger than that. And the question is how many phonons can you put in the mode to change its frequency? Now, if it's a thermal lattice, it can only be a few phonons at best. If you've got a fracture or something, you can do better. Maybe you can get up to 100 phonons or so. I guess my approach to this is if you have a phonon laser, well, phonon laser is like a regular laser, and the thing that a laser does best is to put lots of photons, or in the case of a phonon laser, phonons in a single mode. In the case of lasers, that number can be 10 to the 9th or 10 to the 10th without any trouble. In the case of phonons, there's no reason at all why that can't be true also. People have actually worked on phonon lasers, and they've made phonon amplifiers. In the past, phonon gain has been observed up just to under terahertz. In order to make this work the way I think might be going on in these experiments, assuming that they're right, you'd need a phonon gain a factor of 10 higher in frequency. Okay, so we get down here. We've chosen mode shifting because that's about the only thing that's got a chance of doing the job for you. Then you need many phonons per mode. In order to do that, basically you need a phonon laser. I want to talk a little bit, well, I've talked a little bit about phonon laser. Again, as I said, they've been made in the past, and we know a lot about how phonon lasers would work. People have published a lot of papers on them. Now, if you're going to say that you need a phonon laser, now you need a pumping mechanism for a phonon laser. It turns out in the literature you'll find all kinds of pumping mechanisms. You'll find people running large currents through semiconductors and seeing phonon gain. The current, as it goes through a lattice, couples to the lattice, and it gets the lattice wiggling, and that can give you gain. You'll also find, I haven't listed it here on the graph, but you'll find laser-driven phonon gain. If you have a laser going into a crystal, and you have another laser going into a crystal, and they're at two different frequencies, if you manage to satisfy various sum rules and phase constraints and so forth, you can get gain on phonon at phonon frequencies through something called stimulated Brion effect. And I think that's an interesting way to go. I think that's would give rise to some very interesting experiments.